Okay, so I'm recording this in case you did not get the message that class was canceled. I asked the secretary if they're putting a note on the door, and I never heard back. So I don't know what's happening. So I really hope people aren't just sitting there being like, she must be in traffic. She must be late. But anyway, such is life. Okay, so how much work is required to pump all of the water, or all of the water, yes, over the top of the tank. All right, so here's the picture that you have. And this is kind of what I was alluding to yesterday with that coordinate grid. So you can do a couple different things here. Let's see, work to pump all the water over the top. You can, if you would like, orient this so that your tank is here, or you can orient it so that your tank is here. Personally, I kind of like this one better, just because I don't want to have to deal with the negative values, but it's kind of up to you. And you might think, well, why would she want to center it there when she could center it here? I don't know. I just, to me, it seems like if I don't have to deal with the negative values, it's better. So that's what I'm going to do here. And now I'm wondering if I even can see what the SSM did with this one, because if they did it vertically, yeah, they did it horizontally with a DX, but that's fine. Yeah, so if you looked at the SSM and you were like, how did they do this? Because it's with the DX integral. I don't know. I could look at it later and try to figure it out, but I'm going to do mine with a DY. Okay, so if you're trying to come up with the equation for this circle, you're talking, oh, yeah, technically it is a circle when we're looking at it. Now, you're seeing really what's the bottom half of a circle. If you want to know what the whole circle is, because we're going to need that to write our equation, to find the equation for a circle, you need the center and the radius. Well, you already know that the radius is 4. So we can write an equation for the circle now by putting in the center, which is x minus h squared plus y minus k squared equals r squared is your equation for a circle. In this case, your center would be 0 and then 4. So you would have x squared plus y minus 4 squared equals, and then your radius is 4, so the radius squared would be 16. And then what we're going to do is solve for y to get an equation or solve for x to get an equation in terms of y so that we can use this. Sorry, I have to like manually put people into the meeting, but it looks like it's happening on its own. Okay. So that I can come up with an area function for the layer here. And keep in mind that the layer that we're talking about, and I'm drawing it down here just because we only have water that's filled to the height of 2 meters. But our layer is going to be a disk. So you have some sort of spherical bowl, and when you look down on it, each cross section will be a disk. So when you pull a layer out of it, it'll be a disk. It just, the radius of your disk will depend on how low or how high you go. So we can come up with the bottom half of this equation by saying, let's see, actually what we can do is come up with half of this, and then we'll get a function for, because all we really need is the radius. So we know that we're looking for a layer being a circle, and the area of a circle is pi r squared. So we're just really trying to focus right now on what the radius is, and that's going to depend on how high up or down y goes. So let's go ahead and solve this equation for x. It's like 86 degrees in here. Let me just turn this on and move it back so it's not blowing all my papers everywhere. Oh. All right. So I'm trying to get x equals some function written in terms of y. So I know that x squared is 16 minus, and then y minus 4 quantity squared. It's going to be up to you how you want to write this expression, but we can go ahead right now and just focus on like, okay, let's write it x equals plus or minus, and we're going to focus on the plus side. 16 minus y minus 4 quantity squared. And that will give us the equation for the right side of our circle. Now, we only care about the bottom half of our circle. So let's see. If I'm looking for the radius, then that's going to be dependent on how high up y is, and that's going to be controlling this value of x on the right-hand side of this circle. But of course, we're only worried about what happens from y going from 0 to 2. So we can go ahead and set up an integral now. Oh, gosh, we should actually refer to this as r. The radius is going to be this x distance. And since we're squaring it anyway, that's the nice part. We can get rid of this radical. So we can say that the area of our layer is pi r squared, which is pi times, and then your radius squared is just going to be 16 minus y minus 4 quantity squared. Jump in if you have questions. I feel like I'm teaching to the abyss again. Now, we're of course going to simplify this in order to work on the integral, but let's see what else we need inside the integral first. So to find the work, this is water, right? Rho g. And we're taking that to the depth of the water, which for us goes from 0 to 2. This is kind of why I wanted to take my hemisphere and place it where it's sitting on the x-axis. If I had moved it down, then I'd be talking about water that would be covering negative values, which is fine. It's not the end of the world. You can still do that. I just prefer to not have to integrate over the negative values if I don't have to. And then we're looking at taking our area function and multiplying by h minus y. So I'm going to take pi times 16 minus y minus 4 quantity squared. And then h minus y is going to be the height that at which the water is being pumped out from the bottom of the tank. And for us, that is going to be 4 meters above the bottom of the tank. So I'm going to say 4 minus y dy. So that's your setup. Does anyone have a question here? Terrific. All right, so when I go ahead and multiply rho g, I'm getting 9,800. I also have this multiple pi that I'm going to pull out of the integral. I'm going from 0 to 2. And then I'm going to go ahead and multiply this out. So now I have 16 minus, and then the quantity y minus 4 being squared is y squared minus 8y plus 16. And then this is getting multiplied by 4 minus y dy. Oh, sorry, down there. So we have 16 minus y squared plus 8y minus 16 multiplied by 4 minus y dy. You know, I keep thinking we should probably have, there's probably something easier that we should have done here, maybe with even just factoring out this 4 minus y, or technically y minus 4, but I guess we couldn't have done that here. So, because it seems a little bit messy, but let's simplify it a little bit. So we have 16 minus 16, so those are going to go. And then I have negative y squared plus 8y times 4 minus y dy. And then we'll continue to simplify. So we have positive y cubed. And then if I'm trying to keep these in descending order, I might not even try, but okay, the most I'm going to have is y cubed. And then I'm going to move down here to minus 8y squared plus 32y. What did I miss here? First, oh, I didn't get the minus 4y squared. It's fine. dy. So let's see. Plus y cubed minus 4y squared plus 32y minus 8y squared. And then we'll simplify this one more time. I'm running out of space here at the bottom. I'm going to have to switch over. So this is y cubed minus 12y squared plus 32y dy. And then we'll integrate. So this is 1/4 y to the 4th minus, when I divide by 3, I get 4, and then y cubed plus, when I divide by 2, I get 16, and we'll go from 0 to 2. Two to the 4th is 16, divided by 4 is 4. 2 to the 3rd is 8, times 4 is 32. 2 squared is 4, times 16 is 64. Do I have a calculator up here somewhere? At the moment of truth. That'll be 32 plus 4 is 36. 36 times 9800 pi. And then we'll see what happens. 1108353.888. So this is 1.11 times 10 to the 1, 2, 3, 4, 5, 6 joules. Let's find out. 1.108 times 10 to the 6th joules. Yeah, 36 pi rho g. Okay. So yeah. To recap, we had this hemispherical tank. We said, okay, you can orient it this way so that the bottom half of it is sitting underneath the x-axis, or you can push it up so that the absolute bottom of the tank is sitting on the x-axis. I know this seems harder. Either one. If you would like, you can try this one. And really, it's not going to make a difference to your radius, because, I mean, think about the fact that your radius is going to depend on what's happening on the right side. So when you take a plus or minus here, you're still focusing on what's happening on the right side of the circle, whether it's down there or up there, and it's getting squared. So so that's not going to matter. The only thing that's going to change here is when you write the equation of the circle, it would just be x squared plus y squared equals 16. So the function would change. And maybe now that we've actually done the work for it, you'd be like, if the function changes so that I just have 16 minus y squared, instead of 16 minus y minus 4 squared, we could have saved a lot of algebra. And I guess that's true. In hindsight, maybe orienting it here would have saved us some work down there, just because it would have simplified this radical a little more. So so that's definitely an option. So if you decided to do that, you would have integrated from -4 to -2, which is where the water would have existed in that case. So yeah, did that. And if you want, try it and just verify that you get the same thing. Number 32, I didn't assign, but it's sort of like a follow-up, and it's saying how much work would be required if the whole tank was filled with water to pump it to a height 2 meters above the tank. So the only thing you'd be doing there would be changing the limits of integration. So in case you were looking at 32, if you were pumping all the water out, your limits of integration would go from 0 to 4 if you set it up this way. And then if you were pumping it 2 meters above the tank, then instead of this being 4 minus y, if you set it up like this, it would be 6 minus y. So it's important to note. What else from the homework? Anything else from the homework? I mean, we can talk about volume too if you want. If you're joining us a little bit later, I know it took a while to get on here tonight, and I don't know if some of you, I mean, do we check our ECC emails? Did we find out this morning when I sent the email, or was it a process? I can't get you guys to talk in the classroom like it's going to happen on the computer. Yeah, I don't know. Sorry. I never would have thought that we had gotten COVID. I can't tell you how many times I've gotten the kids and myself tested over the past 2.5 years, thinking like, oh, it's COVID this time, and it never is. It's always negative. And like we had never had it before. And then all of a sudden yesterday, like, I mean, I have this headache, right? And I'm thinking to myself, like, well, I woke up at, after 5.5 hours of sleep, I ran intervals, and it's like 100 degrees outside. No wonder I have a headache. And I get home and my husband's like, oh, I have to go to bed. I have these body aches. And the kids had been sniffling, but the kids are always sniffling. So I'm like, all right, let's just test everybody. And it was COVID. So anyway, so now I feel terrible, but it just was not a thing that I was thinking was even a possibility. But I mean, I guess I knew it was a possibility, but not a likely one. So I do have a sub coming in for you tomorrow. Actually, I had 2 people volunteer. They were both like, if we have to, we'll help you out. So I'm trying to figure out which one to bug. But yeah, so you will have a sub tomorrow to take your test. Nothing too crazy on the test at all. I just want to know, like, do you understand the basics of how to do this stuff? It's going to cover all of chapter 6. Just remember there were really a lot of topics that were covered. Volume was a big one, so you can expect more questions on volume. But like I said, I'm not going to force you on the test to do any volume problems using a specific method. So if you want to use the shell method, or you want to use discs and washers, it's up to you. But you'll find that when you go to solve these problems on the test, they usually lend themselves to one method over another. But absolutely, you can pick. Don't forget about area. Sometimes I start the test out with some 6-1 problems that I feel like will be really straightforward area problems. And then students end up like computing the volume. They like pick an axis and they revolve it. And I'm just like, that's not what I asked you to do. So make sure you're reading the directions. I won't be there to remind you. You will have your trig and your integrals and derivatives sheet that I'll make sure also gets copied to send along to you. you may use a note card 4x6 double-sided, or you may use two 4x6 note cards that are single-sided if you don't want to have to flip them. And since I only have 9 of you in here, I'm missing 4 people from the class. I will send out an email also clarifying this because I want to make sure everyone's aware. What else? Oh yeah, don't forget, we talked about arc length, we talked about surface area. There will be one slicing problem on there. It'll be very similar to some of the homework problems that you did. So if you did the slicing homework, that will really help you on the exam. But a lot of those problems were pretty similar. It's just, you know, pay attention to, are we perpendicular to the y-axis or the x-axis? And then what shape you're looking at. So make sure you know that, like, for instance, if we're talking about like a semicircle, the area of your cross section is 1/2 pi r squared. If you're talking about a square, like the area of your square is side squared. So an equilateral triangle, you know that the height is always going to be √3 times whatever that base is. So yeah. Okay. What else do we want to talk about? Because I also maybe thought we should talk a little bit more about, gosh, I feel bad talking about more 7-1 if 4 people from the class aren't here. So maybe I won't. Could I go over number 21 from 6.5? Yes, Martin. Nice use of the chat, by the way. You can always feel free to use the chat. 6.5. Number 21. All right, so this is x plus 1 cubed equals 4y squared. Y is greater than or equal to 0. And we're looking at this from x equals -1 to x equals 16. Oh, yes, yes. I've been staring at this like, wait, did I mean to assign this? Yes, I did. Okay, so now most of the exercises that you were given in 6.5 have a y equals, but you can go ahead and solve for y in this case, and you're already being told that y is greater than or equal to 0. So, well, getting all these bizarre pop-ups, which is unusual, but they're all from Chrome. Okay. So we'll go ahead and we'll solve this for y so we can get y as a function of x. And then we'll find the arc length, right? That's what we're finding. Arc length, yes. Okay. Okay. So let's see, we have x plus 1 quantity cubed. I want to solve for y. So we'll go ahead and first divide by 4, and then we'll take the square root. So I have 1/4 times x plus 1 quantity squared equals, oh, no, not quantity squared, sorry, quantity cubed. 3 is a little funny. Equals y squared. And then we'll take the square root of both sides, and we know that y is positive. So we'll, instead of taking the plus or minus square root, we'll just use the plus. So officially we're saying, okay, y equals plus or minus this. But because we know that, we're going to say that y equals, first of all, we'll take the square root of 1/4, and you'll get 1/2. And then this will be x plus 1 to the 3/2 power. Remember that when you're changing from radical notation to a rational exponent, the exponent becomes the numerator of the rational exponent, and then the index of the radical becomes the denominator. So we have y equals 1/2 times the quantity, x plus 1 to the 3/2 power. All right, so I know it seems kind of silly, like, why didn't they just give us the function? But here's what we're dealing with. We're trying to find the arc length here. So let's go ahead, and we need a bunch of different things. One of them, the first thing we need to do is find the derivative. Then we're going to square it. Then we're going to add 1, and then we're going to see what happens when we put that under a radical. So y prime is going to be 1/2 times 3/2, and then x plus 1 to the 1/2. Now, this is a situation where in Calc 1 you were taught to use the chain rule. Anytime you have some composite function where not only are you just taking x to the 3/2, but it's now x plus 1 to the 3/2, we need to consider the fact that we have a derivative on the inside function. However, the inside function has a derivative of 1. So in this case, yeah, we can write it and say, okay, we looked at it, we used the chain rule, but you don't have to do that. So now we can go ahead and simplify this out. We have 3/4 times x plus 1 to the 1/2. If you would like, you can also just write this as the square root of x plus 1. It's up to you. Okay, you might want to leave it like that. But I was thinking since you were going to square it, you might find this notation better. All right, so the next thing we're going to do is square this quantity. I'm going to square each factor. So 3/4 squared is 9/16. And the square root of x plus 1 squared is x plus 1. And then we will add 1 to this. Before we add 1, you might want to distribute. I guess I'm thinking we're going to add 1, so we're going to get a constant here. So we might as well just kind of simplify it first. If you have questions, please just tell me what the question is. You can use the raise hand feature too if you feel more comfortable doing that. I know sometimes when I'm in online meetings and I'm supposed to be contributing, I'm just like, I can't contribute because like everyone else is talking and I don't know when it's like appropriate to interrupt. So sometimes I just use like the raise hand thing. Okay, up to you. So I have 9/16 x plus 9/16 plus. Now when I'm adding 1, I know I'm going to combine these together, so I'm just going to call it 16/16. And then I have 9/16 x plus 25/16. And this is good because 25 and 16 are both perfect squares. It might not matter to us that 25 is, but it'll help us out that 16 is. All right, so the square root of y prime squared plus 1 is the square root of 9/16 x plus 25/16. Now, if you're thinking ahead and you know that you're going to put this into an integral, you know that you can technically integrate it like this, but you might want to simplify it first so that you don't have to deal with these fractions. Because you could just do a u substitution here, but then du is 9/16. And I'd much rather have a du that's an integer. So I'm going to go ahead and simplify this by saying it's the square root of 9x plus 25 over 16. Might as well just keep that same denominator. And then I can simplify this by taking the square root of the numerator and denominator separately. And then the square root of 16 we can write as 4. Okay, so back to our original, we knew that x was going from -1 to +16. Let's see. Oh, you know what? I didn't even check. I told you I wasn't going to give you any problems where it wasn't the case. But remember, we technically need to verify that our derivative exists on this interval. And note that when you look at your derivative, if you were to plug in values anywhere from -1 to +16, you wouldn't have any issues with the derivative not existing. However, anything less than -1 would cause a problem because you can't take the square root of a negative number, but you can take the square root of 0. So that's our lower bound, and that's okay. So your arc length is on the interval from -1 to 16. I'm going to take this 1/4 and pull it out front so I don't have to look at it inside the integral. And then I have 9x plus 25 dx. And for this one, I'll use a u substitution. So I'll let u be 9x plus 25, and du is 9 dx. That means 1/9 du is dx. I'm also going to change the upper and lower limits of integration because that's what we should be doing. I have x equals 16, x equals -1, and I know that u is 9x plus 25. Where's my calculator here? All right, so I have 9 times 16 plus 25. That's a large number. It's 169. And then the other one is just -9 plus 25, which is 16. So I'll go from 16 to 169. So I have 1/4 times, and I'm going to put this 1/9 in front because that's part of the dx substitution. I'm going to go from 16 to 169, and I'm going to take u to the 1/2 power du. And like I said, if you guys have questions, let me know. All right, so 9 times 4 is 36. I know that if I integrate u to the 1/2, I get 3/2, or 2/3 u to the 3/2. So I'm going to multiply by 2/3, and then I'll have u to the 3/2. I'll evaluate that from 16 to 169. In the denominator, I get 54 here, and then I have 169 square root 169. I'm only doing that because I already know the square root of 169. So I figured writing it as a 3/2. You could evaluate it in your calculator, but I thought it'd be better to write it like this. And then minus 16 root 16. And I'm like just out of space. So let's see. Move this down. This leaves me with 1/54 times 169 times 13 minus 16 times 4. Now I'm going to get my calculator out. So 169 times 13. Yeah, technically you could have put that in as 169 to the 3/2. I know. I just think it's good for us to do this very slight bit of mathematical gymnastics. Times 13 times 4, and then I'll divide that by 54. I don't know if 54 is a factor. We'll find out. No, I get 39.5. So that simplifies to 79 halves, which is your arc length. All right, so we did a word problem. We did an arc length problem. Are there any questions on the arc length problem that we did? Okay, what else do we want to talk about then? Don't be shy. I could talk about volume. Oh, slicing with a triangle. Homework 6.4, number 5B. Let's look at it. 6.4, 5B. Okay. All right, so 5A with semicircles. So you're okay with the semicircles? Did he say anything else? No, nothing else. Sometimes the chat doesn't beep at me. So if you do chat and I don't see it, let me know. But it seems to be beeping tonight. I think maybe it's if I have the chat open already, then it doesn't beep at me. It assumes I see it. I don't. There's a lot going on over here. 6.4, number 5B. So if anyone had a question on the semicircles, we can set this up for B, and then we can talk about what would change if we were talking about semicircles versus the equilateral triangles for part B. Actually, I was trying to, oh, you know what? When we did equilateral triangles in class, our base, what's our base? I'm looking back at this. Oh, our base was the unit circle. So same idea, but different base. Pencils here. All right, so it says the base of your solid is the region enclosed by the graphs of y equals the square root of x and y equals 1/8 x squared. These can be kind of hard to graph. I'm going to try to do it on my usual 3D coordinate grid, and we'll see if we can see it. I think we'll be able to see it just fine. All right, so we have y equals the square root of x. If you want to see the 2D view first and then translate it on, I think that's how we were doing it in class. Y equals the square root of x was the first function. It looks like this. And these two are our region's going to be bounded by both of these. So technically our 2D graph will sort of give us a clear picture of what the base looks like, and then we'll just have to switch it on over here. Really important to label my axes right now. The other one was y equals 1/8 x squared. To graph this one, I would probably just plug in some points. If you let x be 1, it's going to be a little bit hard to see. But we can see that if x equals 0, we have a point here at the origin. If x equals 0 and y equals 0. If x is 1, y equals 1/8. So you know that this is like really small, super small. When x equals 2, well, now we get up to 1/2. I should have scaled this a little bigger, but you can kind of get a sense for what this looks like. And you can even graph it in your graphing calculator to check. And then 3 squared is 9. So we're up to a little bit more than 1 here. And then 4 squared is 16 divided by 8 is 2. So you end up getting these two graphs to intersect at the point 4, 2. This one is y equals 1/8 x squared. So this is what your base is going to look like. So we're going to, all we really need here is this first octant. And we're going to sort of translate this over. So I'm going to go, I know I just need to go up to 4. So I'll just label the x-axis from 1 to 4. If you want to plot some points, you can. We know y is only going up to 2. So I'm going to try to just keep it evenly scaled. I think the picture is large enough to do that. Okay, so we're going 1, 2. So we have a point at 0, 0. When you're graphing your square root function, you know you have a point at 1, 1. And then you know you have a point at 2, 1, 1, 4, 2. 4, 2. I'm looking at this kind of upside down, as are you. So here's your radical function. And then the other function, I mean, it doesn't have to be exact. You have a sense for what it's doing. So you know it kind of comes up like this. And we'll call this y equals 1/8 x squared, as long as you know that these two are intersecting at this point 4, 2. All right, so that's your base. And the book gives you a picture too. It gives you the picture with the semicircles. So we'll go ahead and just put the triangles on here. It says to find the volume if the slices made perpendicular to the x-axis have cross sections that are equilateral triangles. So we're slicing perpendicular to the x-axis, which means we're slicing this way. perpendicular to x. So we're going to do the same thing over here. If we slice perpendicular to x, we're going to be parallel to y. That does not look parallel to me. Do the best you can. The nicer your picture is, the easier the problem will be for you to do. Okay, so it kind of looks like that. And you can imagine how you're going to get these equilateral triangles that are going to be built off of this base. And they're going to get progressively taller as you move your way to the center of this region. Just because the base length is a little longer, the distance between those two curves is at its greatest in the middle of the region. And then as you start to head back towards the end of the region, these triangles get smaller again. So what you end up with is this 3D region that kind of looks like that. If you can see that. Okay. So what I need to know here is the area of the triangle. And I know that the area of a triangle is 1/2 base times height. So I'm going to go ahead and put the base down because I already know what the base is. The thing is, the base is going to be a function that depends on whatever value you happen to be sitting on that region. So we're going to have to write the base as a function of x. So no big deal. We know how to do that because you've been doing all this top minus bottom work as you've worked your way through this chapter. Here we go. Got it. There's ND. Okay. Hi, Savani. We're talking about 6.4, number 5B. We're just reviewing, and I'm also recording this, so you'll be able to catch whatever you missed later. And the test is tomorrow. We're getting a sub, so you're caught up to speed now. If you have a question, let me know. All right, so we're oh, no problem. I'm sure a lot of people joined late because not everybody got my message earlier. Fine. I understand. It's an in-person class. You're not thinking that anything is going to happen. Okay. So the base of our triangle is going to be, oh, and by the way, wait, I said we are perpendicular to the x-axis. Remember, we made a big deal about this. If we're perpendicular to the x-axis, we need a dx integral. So perpendicular to x-axis, I should have made a big deal about that at the beginning, means that we need a of x and dx. So we're looking for the integral from a to b of a of x dx for our volume. Okay, so the area of our cross-section is going to be dependent on the length of its base. So let's go ahead and find that. We need to write y as a function of x for the base. That's good. Now, you are asked to do something similar, and maybe it's in number 6, which I didn't assign, I think. Yes. So in number 6, you get the same base region, but the volume is being found when the slices are made perpendicular to the y-axis. So in that case, for number 6, you would have to rewrite these functions as functions of y instead of functions of x. But in this case, it's really important to note that we're dealing with a dx integral, and we're looking for a of x. So you know that you don't have to rewrite these functions. They're right already where they need to be. So the base, let me just do that first. The base of each of these triangles, and if you think about it in the 2D variation, is going to be the length of the top function minus the bottom function. The top function is the square root of x. The bottom function is 1/8 x squared. So we have that. And then remember we talked last time about this triangle. Let's see. And last time we kind of split it up. Let's see. I split it up into twos because I was using like 1/2 of your base length. But so let's see. We took our triangle. Then we said, okay, well, if I was looking at half the triangle, the height of the triangle would be √3, the base would be 1, and then, oops, sorry, and then your hypotenuse length would be 2. And what you are doing in this situation is you're actually including both pieces of this as your base. So you're not just thinking about, gosh, I'm trying to remember why this came up last time. Oh yeah, because our base was a circle. So we took like half of it and then we multiplied it by 2. So we took, yes, that's why. We took twice the base and then the height was square root of 3. I'm looking back at my notes to kind of compare this to what we did. But this time we're using the whole thing as the base. It's not like we're only taking half of it, which was split. So if we're using the whole thing as the base, that's fine. We can say that in this case, if this was half of our base, considering your base was 1, then we could divide all of these sides by 2, and then the height of your triangle would be the square root of 3 over 2 multiplied by that base length. Because you're not just taking half of it anymore to get that distance, you're taking the whole thing. So it's almost like you would be taking this same equilateral triangle, and instead of saying 2, 2, 2, you'd be saying 1, 1, 1. Well, if I call it 1, 1, 1 and I split it up, now I have a half. This side didn't change, it's still 1, but now that side would get divided by 2 also for your height. Does that make sense? So it's important that we understand the difference of when we're just multiplying by the square root of 3 and when we're multiplying by the square root of 3 over 2. And that's just because your base, the whole base was covered, not just half of it by your function. So we would say that the height of our triangle would be the square root of 3 over 2 times the base. And now we'll have 1/2 the base times the height, and we can integrate over this region from x equals 0 up to x equals 4. So let's go ahead and set it up. And then if you have questions, please either raise your hand or chat me or something and ask me to clarify, because I can't see any faces. So I don't know if anyone's like, okay, this makes sense, or like, I have no idea where this stuff's coming from. I think the triangles, though, the equilateral triangles are always the trickiest. Yeah, so I will absolutely clarify the triangles again. And I think it might make the most sense if we kind of compare it to what we did in class. So let's do a side note. In class, I did example 1. And in example 1, remember we had, you can look back at your notes for this, but I'll try to make this look decent. It took us some time to graph this in class, but we did a unit circle, and then on top of it, we built these equilateral triangles. Okay, so that one had this base, that one, so on and so forth. Okay, so we had something like that for example 1. And then when we were trying to find the area of the cross section, that area of the triangle, when we looked at this in a 2-dimensional view, right, we were doing this with respect to, oh yeah, the x-axis. So it's almost like we took this view and we rotated around. So, I mean, it's a unit circle, so you kind of have already a sense of what it's going to look like. But here's your base. And then we said that, all right, we had this written as y equals the square root of 1 minus x squared. When we built a triangle off of that, the base of the triangle covered this whole distance. So what we did was we found the length of half of the base, and then we multiplied it by 2. So we said in class, looking back at my notes so that I know what I said in class. Let's see. So we were like, okay, fine. The area was, oh yeah. So we did 1/2 times base times height, but our base was twice the square root of 1 minus x squared, because we were looking at this being half, and then we said, okay, well, the base is going to be twice that. And because the base was twice that, it made sense to use this triangle, because this triangle multiplies this base by 2. So whatever the base is, I mean, you get this proportional relationship between the sides. And then we went from there to saying, okay, well, if that's the case, it's not even an equilateral triangle anymore. Like, let's split it in half. And then if we did that, like, we would no longer have 2. This would be still 2, but this would be 1. And then we solved for that side. And that worked for us because we were looking already at multiplying the base length by 2. In this case, we're not multiplying the base length by 2 because we don't have that same situation. What we have here is just that the base is what you see. It's not getting multiplied by 2. So for that, it makes sense to use this variation of the triangle, where this is the whole base length. And then if we say, okay, well, I just need to find the height of the triangle, I can just take it in half, solve for the missing leg length using the Pythagorean theorem. And then in that case, I'm just taking that base and I'm multiplying it by root 3 over 2. So it was really just a matter of what worked best for us. But you can technically use either triangle. You just kind of have to note, like, wait, am I multiplying this base by 2, or am I getting the whole base just out of the picture? Okay, cool. I was afraid that you were going to come back and be like, that sounds like craziness. Okay. But that's the big difference. In general, when you're talking about equilateral triangles, the height is always going to be root 3 over 2 times the base length. So maybe you want to write that as a note. In general, for equilateral triangles, the height is root 3 over 2 times the base. But when you make the base 2, then the height is twice root 3 over 2, which is root 3. So this is a general note. If you're multiplying the base by 2, then the height is just going to be the square root of 3. Does that make sense? Okay. Does anyone have a question still about the height? I will also scan and post these notes online. Oh, that just reminds me. I totally forgot to scan. No, I remembered to scan, but I forgot to post quiz to key. So I got to do that too. So yeah, I'll post these just because not everybody's here. I think we're missing 3 now. So, which is unfortunate, but that's okay. I think they didn't know what was happening. But come to class tomorrow. We're not doing the test online. You're doing it in class. I have a sub for you. I have 2 reluctant subs that only just want to help me. So they're very nice and they're friends of mine. And also they are mathematical geniuses, but they can't answer any test questions for you. So don't ask them for help. But they will make sure that you have everything you need. And unfortunately, though, because you're going to be taking the test in person and I'm at home, I'm not going to get your test till I come back on Monday. So I won't have them graded till Tuesday, but I'll grade them overnight. I promise you'll get them back Tuesday because I don't want it to take forever. So that's the unfortunate part. If gas wasn't so expensive, I wouldn't mind driving into ECC to pick them up. But actually, technically, I'm not supposed to be like leaving my house for 5 days, which is a bummer. So yeah, never mind. But driving all the way to ECC just to pick up tests, even if I could, it would cost a lot of money. Oh, we have to finish this problem. Okay. All right, so let's see. I have this information written up here. We're going to translate it down. So the area function is 1/2 times the base times the height. And this is just going to require a little bit of simplification. And then we'll put it into the integral. You can put it in the integral now if you want, but you have to simplify it first. And I feel like at this point, we're good on this, but just want to make sure. Let's FOIL this out. You'll have x, and then you'll have minus an eighth, which is minus 2/8, which is minus 1/4. And then the x's would give you 2.5, so that's x to the 5/2. And then plus 1/64, x to the 4th power. And this is 1, 2.5, 4. So it makes sense that they're all increasing by the same amount. So if you're doing like a quick check, that should make sense. And then this will just be a constant that you'll put in front of the integral. And now you can go ahead and find the area. Or I'm sorry, the volume, not the area. We're going to integrate over the area function. So the volume is going to be the integral from, and remember, we're looking at what's happening on the x-axis because we have a dx integral. So we're going to go from 0 to 4. Now, I had mentioned earlier, if you are doing number 6, where you're doing the same problem, but the slices are perpendicular to the y-axis, then you'd integrate from 0 to 2 because you'd have a dy situation and a dy integral, dy limits. And by the way, these are functions that are really easily solved for x. So doing this with respect to y is going to be really similar. You're doing the same thing, but with y functions, which is why assigning too much of it on the homework is like you start to basically just repeat the same numbers and then you're not thinking about it anymore. So it doesn't make sense to assign all of them. Then it's just copying. All right, so from 0 to 4, we said we were going to leave that outside. We'll have x minus 1/4 x to the 5/2 plus 1/64 x to the 4th dx. And then we'll integrate. So this is 1/2 x squared. 5/2 plus 1 is 7/2. So we'll have 1/4 times 2/7 x to the 7/2. Plus, and then we'll divide by 5. 64 times 5 is 320 x to the 5th from 0 to 4. And then we'll just use the FTC. 4 squared is 16, divided by 2 is 8. Here you get 1/14 times 4 to the 7/2. That's 4 to the 3.5, which looks like this. 4 to the 3rd, 4 to the 1/2. Again, you can put that in your calculator. I just like to not have to use my calculator if I can help it. 4 to the 5th. Well, here I am using my calculator now. I don't know, 1024. That's one that if I use it a lot, it sticks with me, but I don't always use it a lot. And then the lower limit of integration, because you have a polynomial, is 0, so we don't need to worry about evaluating at the lower limit. So we'll just continue to simplify. You'll have 8 minus 4 cubed is 64 times 2 is 128. And then plus 1024 over 320 simplifies to 16/5. And at this point, you might as well just say 8 minus 128/14 plus 16/5 is 72/35. 35ths. And then 72 35ths divided by 4 is 18 35ths. Times the square root of 3. Please tell me that's the answer. Yes, it is. Okay. All right, so we did an arc length problem. We did volume by slicing using equilateral triangles. We did a work problem talking about a spherical container. Is there anything else you want to go over? Six, 5, number 19. Sure. Yes, James, we'll do that. Oh, 6, 5, 19. Did I say 6, 4? I don't know. 6, 5. Okay. Okay, number 19. Here. Trying to organize all these notes so I can scan them for you guys later. Y equals the natural log of the sine of x. And we're looking at that from x equals pi over 6 to x equals pi over 3. Okay. This is a really good one to go over because a lot of times students forget about taking derivatives of natural log functions. And this came up, but I'm going to double check. There was one. Oh, no, you know what? I think the derivative is included on your integrals and derivatives sheet. I have like a bajillion pieces of paper in here. All right, here it is. Found my integrals and derivatives. It is included. So it's number 9 for derivatives. Where it wasn't included was for the integration formulas. So we don't have an integration formula for ln x. That's something we have to use parts to integrate. But you do have an integration formula that says the integral of 1 over u du is ln x. And that's not on there. But I mentioned to you to put that on your note card. So in case you need it. But anyway, that was the side note. So let's take y prime. Oh, I'll remind you of number 9. This is on your, I always call it cheat sheet. Number 9 says that d dx of ln u is u prime over u. So it's the derivative of the inside function divided by the inside function. So let's go ahead and find the derivative of y. So the derivative of the inside function is cosine x, and then the original function is sine x. And if you remember from taking these logarithmic derivatives in Calc 1, a lot of times you were like, wait, this doesn't make sense. What happened to the natural log? It's gone now. It's supposed to be. So I know it's very upsetting to students. They don't like that. But remember that when you take the derivative with your natural log function, unless the natural log is inside of another function, it's going to go away. And that's okay. You have to accept it. And if you were one of those people whose Calc 1 class did not cover transcendental functions, you've seen it. Hopefully you at least covered them for derivatives. At ECC, we never used to cover them until Calc 2. We did derivatives and integrals. We would start out by just only focusing on derivatives and integrals of transcendental functions. But then they changed the way the course was structured, and it was covered in Calc 1. We added a credit hour to it, and the rest is history. Okay, you might be looking at this, and you might be thinking like, well, I could change this using something that I know about. What am I thinking of? A reciprocal function. Are they called reciprocal functions? Reciprocal function. No, it's called tangent and cotangent identities. Cosine over sine is cotangent. If you would like to use a cotangent, that's fine. I tend to think that students don't like using cotangents, but in this case, you might find that it's helpful. But if right away you're kind of like, I don't know if I want to do that, that's fine. We can go through without using it. Do we want to use a cotangent? I think I'll switch mine. I think I will. Because, okay, think about it. Get a game plan for what's going to happen. If we know that we're going to take this and square it, we're going to end up with cosine squared over sine squared, and then plus 1. So we'll have cosine squared over sine squared plus sine squared over sine squared. You can still do it because in the numerator, you're going to have cosine squared plus sine squared is 1. And in the denominator, you're going to have just sine squared. I don't know. It might be more beneficial for us to switch this into just one function. So let's do that. And we'll see if we can use some trig identities along the way. Okay. So this is y prime. Now we'll take y prime and square it. So when we square the cotangent of x, we just get cotangent squared of x. And then when we add 1, we'll get, I used to always, when I taught trig, I always called this cot squared plus 1. I don't know what you always had it referred to as. You maybe didn't even see it a lot. But if it looks familiar to you, it should, because if you look at your Pythagorean identities on your trig sheet, it's on here, Pythagorean identities. 1 plus cot squared is cosecant squared. And if you're one of those people who doesn't like to use cosecants, like, okay, but might want to see where this is going, because now we're going to take the square root of y prime squared plus 1. We're taking the square root of the cosecant squared of x, which is the cosecant of x. All right. Let's go ahead and set this up into an integral, and then if we need to backtrack and put this back into sines and cosines, fine. But I think you're going to end up in the same boat regardless. And if you're not sure why, I mean, think about what would have happened if we had set this up with sines and cosines. If you had done that, you'd say, okay, well, y prime is cosine x over sine x. Y prime squared is cosine squared over sine squared. When you add 1, y prime squared plus 1, you get cosine squared x over sine squared x plus, and then you can just call 1 sine squared over sine squared. And what you end up getting is cosine squared plus sine squared is 1, and the denominator stays the same. Well, then when you take the square root, you're taking the square root of 1 over sine squared x, which is 1 over sine x, which is the cosecant of x. You're going to get there one way or another. So it, I guess, really doesn't matter how you get there. I say all that to say that this is going to be what's inside your integral. Do I have space here? Okay, so we're going to integrate from pi over 6 to pi over 3. And you don't have to worry about your derivative not existing on this interval. It does. There is no value between pi over 6 and pi over 3 for which sine of x does not exist. So you're fine there. And then the square root of y prime squared plus 1 is the cosecant of x dx. Now, maybe you got all the way here and then you were like, wait, what do I do? I believe this is on your formula sheet. It is. So number 11 is the integral of cosecant u du. Now, I also think that there are two different forms in which to write this integral. So it's possible that you saw one variation on your formula sheet and you were like, wait, they got a different answer. Yeah, your book does, I think, use two different formulas. So I'm going to give you number 11 on your formula sheet. And if you were one of those people who's like, I don't get why my answer didn't match, I'll tell you the equivalent way of doing this. So on your trig and, or I'm sorry, on your integrals and derivatives sheet, the integral of cosecant u du is negative ln cosecant u plus cotangent u plus c. This is fine, absolutely fine to use. When you were introduced to this in your book, and it might even be different in the back in the table of integrals, it was way back when you were talking about, I want to say it was 4.8, which if you didn't take Calc 1 here, you'll be like, huh, what's she talking about? So I'm going to tell you right now. The formula is probably slightly different. The antiderivative of the, I know those are just like straight ones, those aren't formulas. 5 point something FTC. I don't know. Anyway, there's another form for this. Get the back. I think I remember what it is though. The negative goes away and it becomes ln cosecant u minus cotangent u plus c. Verify that. Until I don't use these a lot. But if you go to the way back of your book, you'll see a bunch of integral tables. We're going to use those in 7.8. So they're not things you are supposed to be using, but they have general ones. The pages aren't even labeled. It's the way back of the book. And they give a basic integral for the cosecant of x dx as ln cosecant x minus cotangent x plus c. I hate the way they do x's and not u's. Drives me bonkers. But either one of these is fine. So if you were like, wait, my answer looks different, don't worry. And for a definite integral, you should be able to get them to match up anyway. I'm going to use, I'll just use this one because the minus sign is built in. All right, so it's just cosecant x. So we're going to take ln cosecant x minus cotangent x, and then we're going to take that from pi over 6 to pi over 3. There's no substitution here, so that's kind of a nice change of pace. So this is ln. And then since you're going to be evaluating these, most of us off the top of our heads don't know what the cosecant of pi over 3 is. Change it to 1 over the sine of x. And then probably with cotangent, you might know the cotangents. You could, if you know the tangents, you could switch that to 1 over tangent. If you don't feel comfortable with that, just call it cosine x over sine x. As long as you know the cosines and the sines, that's really the most important thing. But you got to know those. They're basic. All right, pi over 3, 1 over the sine of pi over 3 minus the cosine of pi over 3 over the sine of pi over 3 minus 1 over the sine of pi over 6 plus the cosine of pi over 6 over the sine of pi over 6. And we have absolute value bars here. You know what, too? I was just thinking, Ellen, I don't know if it's going to matter. This. Yeah, I'm gonna write this the way it's supposed to be rewritten because I can't technically like factor that out. So this would be the ln of the upper limit minus the ln of the lower. I don't want to do anything crazy here. All right, so we have ln, the sine of pi over 3 is root 3 over 2, so that's 2 over root 3. The cosine of pi over 3 is a half. And then that one we'll simplify. And then minus ln, the sine of pi over 6 is a half. And then plus the cosine of pi over 6 is root 3 over 2. The sine is a half. The 2's here cancel. So this is 2 plus root 3. And then we'll just simplify this a little bit. You might be like, well, exactly how much simplifying do I need to do here? Normally, oh, you know what? I just caught something else weird that I did. Hold on. When I subtracted here, I should have switched this sign back because I'm taking the upper limit minus the lower, and now the inside function's not changing anymore. Sorry, these should be minus signs. Minus, minus, minus. It's not a huge deal, but it will change your answer, make it different. All right, so what you'll see a lot of times with natural logs is that your book is going to write them as the natural log of one quotient using that rule for natural logarithms and subtraction. So if you have ln A minus ln B, your book usually will write those as ln A over B, which is a logarithm rule from your Algebra 2 class. So I'm not too much of a stickler about that as long as you have the answer. I mean, I like for it to be simplified, but at some point, like, you can stop simplifying, you're done. But let's go ahead and just simplify this one a little bit more. So 2 minus 1 is 1. So you have 1 over the square root of 3 minus the natural log of 2 minus the square root of 3. And then there are all kinds of different things you could do to this. If you got this far, I'd be happy. 2 minus the square root of 3 is actually a positive value because the square root of 3 is like 1.73-ish. You could drop the absolute value bars at this point because you already know the quantity is positive. Same here. It's a little notational thing. It's not the end of the world, but you don't. It's redundant. Like, it's already positive. Like, we don't have to keep telling everybody it's positive. This is fine. If you wanted to rewrite it, you could say the natural log of, I don't know, because sometimes it really is about just matching what the book has done of this. And then technically this is a complex fraction. To simplify a complex fraction, you multiply every term by the LCD. The only denominator you have here is the square root of 3. If I took this out for a second, you could see that a little bit better. Multiply the numerator and denominator by the square root of 3, and then you would get 1 over, and then the square root of 3 times 2 minus the square root of 3. And you could do it that way. I'm running out of space here again. And then you'd probably want to multiply it in because these radicals will simplify to 3. I mean, really, you could go on for a long time doing stuff to this. This is in the denominator, so you could write it as a reciprocal to the negative first, and then you could use the power rule to bring that down. I mean, there's a lot you can do here. They're all the same. Should the answer still be the same if I use the other variant? Yeah, so you can do it if you want, if you use the other variation that we had on the sheet. You would be able to get the same answer. You might just have to manipulate it a little bit more in order to get there. Because really what's going to happen is this is going to be negative and the terms are going to be switched in both cases. So then it's almost like you could just switch these two because the integral would be negative. You'd be switching the limits. But yeah, you should still technically be able to manipulate it to get it there. But when there are things that occur like this, there's another one that does this. Which one is it? I can think about which one it is. Oh yeah, I think it's number 8. Let me check. There's another one you can write 2 different ways. And then depending on the way you write it, number 8 is, you can go with tangent. I mean, you should still be able to manipulate it. Yeah, so on your sheet, number 8 is the integral of the tangent of u is negative ln cosine u. But in the back of the book, and I think this is how they introduce it, and it might even be in 7.2, I'm not positive, is ln of the secant of x plus c. And the reason that works is just because of this rule for logarithms, the secant and the cosine are inverses. So you could technically reverse the numerator and denominator and make the function negative, which is why you have more than one form for those. It's just a shame that the books can't agree on which form they want to use. But yeah, you should always be able to manipulate it and get it to match the book problem. But I guess it's frustrating for you because you're like, oh my gosh, is my answer right? I don't know. Or you could take the book problem and make it match yours. What does the back of the book say for this one? 6.5, number 21, no, number 19. It leaves it as natural log root 3 over 3 minus the natural log of 2 minus root 3. So yeah, the back of the book basically leaves it like this, except they rationalize the denominator and they drop the absolute value bars because, like I said, it is redundant. I'm not too concerned about it. When these pop up again in chapter 7, you're going to be seeing a lot of these trig integrals where you pick a form. I'll accept either one. And there'll be a way that I write it on the key, but then when you do your exam, if you pick a different form, as long as it's a valid form, it's fine. Sometimes even when I write the exam key, I'll say like, okay, this is good, like, or you could have written it like this, just because it's easier for me to grade it knowing what the alternate answers would look like. So a lot of times I'll write a bunch of different forms just so I can look when I grade it and see like, does it match one of these? If not, like what happened when I go back, figure out where the problem lies. So yeah. So yeah, you should, the answer is the same. It's just they're equivalent. You just need to make them look the same. All right, anything else from chapter 6? I'm not going to go into chapter 7 tonight. I'm missing some of you, and I don't feel comfortable moving into the rest of chapter 7 without everybody being here. Because then it's like, oh, well, I didn't sign up for an online class, and now I got to watch this on my own time. So I don't want it to be like that. You guys probably see so much of me just staring at you being like, anyone have a question? I mean, if you don't have questions, yes, James, go ahead. You can say it or you can chat me.
Yeah, so on 6.6, like number 17, when I was looking at like the handout of like the solutions, it didn't seem to like use like the gravity variable when I was trying to do it. So I wasn't sure what was up with that.
6, number 17. Oh, yeah, okay. So the deal with 17 is that when you're dealing with units that are not metric units, the weight uses gravity already like factored into the unit. So when it says pounds per feet cubed, weight includes the mass and the gravity. So that's a really good question. I forgot that was a thing that popped up. Let me see here.
So is that like something we're gonna have to worry about on the test or no?
On the test, I will give you metric units because I'm not trying to throw anybody off on the test by being like, here's something new. I mean, not that it's like a crazy topic, but maybe it's something that you've just never learned before, and I don't want to throw that at you. So let me see. So they had the 62.42, and then they just multiplied it by 144 to get, yeah. So weight includes the force of gravity. Mass does not. Mass is usually what they use in metric units. So yeah, I'm really glad you asked. It's possible that in the section they say something about it, but they might not. They might just be like, well, the students have probably seen this before, but a lot of students have not seen it before. The weight of the object times the distance lifted. The weight is rho GV. And they again use meters, kilograms per meter cubed. I'm trying to see if there's like a note about it even, and there's not. So that's unfortunate. Yeah, but weight technically is your rho G, if you see that. Yeah, I mean, it's a good problem to do, but I can see how it's confusing because of that. So I'm going to make a note actually so that I can see it next time I go to assign this problem. Yeah. Okay. Other questions on chapter 6 or anything for your test tomorrow? Okay. If you want to stay on, if you have more questions, if you want me to give you some like volume examples or something, stick around. If you don't, I don't want you to feel like, okay, well, I don't have any questions and now I'm just sitting here. That's fine too. I'm not gonna do any 7-1 tonight because like I said, I don't think it's fair to make everybody watch it on their own time. So that's fine. We'll finish 7-1 on Monday. Your test tomorrow will be over chapter 6, as we discussed. I won't be there. You'll have a sub there. I'll be back on Monday. Yeah, but that's it. So stick around if you have questions. Otherwise, I don't have anything else for you. And I hope you have a wonderful weekend. And good luck on your test. You too, Constantine.
I have a quick question about like the test.
Yes, go ahead.
So, in terms of like, I know like we don't have any like test review questions, but you did mention that like there is like questions that review like the whole like chapter from like the end of the like textbook or something like that. So would there be like any like specific questions you would like recommend that we do from that?
Let's see. Because yeah, let me look. I mean, some of it I feel that shells and discs and washers, like there's a ton to do in those. So like I could technically give you some volume problems, but you might feel like, okay, I don't need any more of those. But let's see if there's anything else. Let's see. So the chapter review is on page 496. It's like, yank, it's right here. And it's got like this blue edge to it. So let's see. I mean, any of these area problems would be fine. Number 3 would be good because it has x equals types of equations. So I can write these down. It's page 496. I'm going to write it down actually. So area is 1 through 5. The answers to the odds are in the back. Volume, I mean, like number 9 would probably be nice because that's xy equals 1. So you'd have a little bit more liberty for like, well, what do I want to do with this function? Kind of depending on what the graph looked like. Mm-hmm. But definitely through 11, I won't give you anything y squared equals 8x about the line x equals 2. Well, it's an even anyway. So I guess technically any of those would be good. I probably wouldn't do anything like 15 y squared equals x cubed just because both sides have the exponent on it. I wouldn't do that on a test. So maybe you could go up to 13. And then for arc length, 17 would be a great one to do. You probably saw some like that in your arc length section. Let's see. Find the volume of the solid generated by revolving the region bounded by the graph and the first quadrant about the x-axis. Number 22 looks very much like the problem I did in class with a different radius. $25 would be a good one. $29 is another hemispherical tank, so it would be kind of similar to the one that you guys asked about in class today. I think Eric asked about. It was number 31 in 6-6. So on the review, 29 would be sort of similar to that.
Okay, sounds good.
Yeah. Find the volume generated when the triangular region is revolved about the y. I mean, surface area, like 39. So, I mean, all of these would be good to do just to sort of solidify, like, do I know this? What do I need to work more on? So on and so forth. And the answers are in the back, and you'll also find them in the Student Solutions Manual.
Okay, sounds good.
Okay.
Yep. Thank you.
You're welcome.
All right, have a good weekend.
You too. Jared, did you have a question?
I did. So I was looking through and I was realizing that there's some questions that I get a little bit stumped on, and that's the ones where they don't specifically tell me where the range of in 6.1 on 17 it was saying that they didn't give me really a bound for how much of because sometimes it'll stop at the x-axis and then you just have to calculate the area through that. But because when I first read the two graphs that it was going through, my brain stopped it at the x-axis when I should have gone beyond it, as the book was saying and the answer thing. And I was wondering if there was a aside from should I when looking at these kinds of things, should it be try to go towards the graph unless specifically stated that it stops at the x-axis?
Yeah, I mean, that would be a good way to look at it because a lot of times we do naturally just try to cut it off there. I remember last semester in particular, I had students cutting things off there, and I was like, why? I didn't give you that as a bound because our brain does naturally just be like, okay, that's a boundary, even if it's not listed. Because maybe even because when you graph it, it looks like a boundary, even though it's not. So, yeah, I'm looking, it's x equals y squared plus 4. That's like this, right? X equals y squared plus 4.
Yeah.
And then the other one was y equals x minus 6. So 1, 2, 3, 4, 5, 6. Oh, I see. So you were like, okay, let's find that
Yeah.
instead of like, let's find that.
Because another thing is that because I have this calculator, the TI-84 Plus,
Mhm.
and when doing it in the when changing it from y equals x plus 1 or something like that, I want to find the
Mhm.
other one where it's
Mhm.
x equals. Is there a way to put that into my calculator so that I can see that as an equation in a graph, or is it more of a I have to kind of figure that out by drawing it?
Yeah, you have to solve for y and then you put in your calculator. So the problem too is if you solve this for y and then you forget the plus or minus, well, you're only going to get the top half of your parabola. So there's no way that I know of, because if you're in function mode, this is technically not a function. There's no way to graph an x equals.
Okay.
Yeah.
So
And
if I have plus and minus for the square root in the equation in the calculator, it should give me the full parabola.
oh, you're asking about the plus or minus button. Is there a plus or someone told me there was a this is like going back into the recesses of my mind. Sorry, I have a calculator somewhere. There it is.
I'm just trying to figure out if there's a way that I could solve this that's not like gonna give me the wrong graph function so that I don't do it on the test and be like, why did I get this wrong? I put it in the calculator and I
Well,
got this as the graph.
yeah, I mean, and the only way to avoid that is just by remembering if you take the square root on both sides to do a plus or minus, because there's really no other check for that. But I mean, also noting that if y equals x squared, you have a parabola. So if x equals y squared, you also have a parabola. It's just sideways. And you'd be like, wait a second, I only graphed half of this. That doesn't look right.
Okay.
Is there a plus or minus button? I
I
could have sworn someone told me that, and I forgot about it until. Is it in? I don't know. I don't know if there is a plus or minus button.
know that there is like
Yeah.
a normal plus and minus, but I don't know if there's one that's like specifically both.
Well, plus, if you don't remember the plus or minus anyway, you wouldn't even know to enter it using the button. So, I mean, if you were going to graph that, you would have to just say square root of x minus 4 and then negative square root x minus 4. And then you would just graph it in those two different parts.
Okay.
Yeah. So it
I guess I'll
really is
just have
just
to
remembering that.
do the math so that it's correct, and then put minus, and then the square root, and then the plus, and then the square root, or just not put anything
Yeah.
in the square
I
root.
mean,
Okay.
if you're at home, you can use Desmos. Desmos graphing calculator will graph an x equals, but you obviously can't use that in class. So I wouldn't depend on it because then you'll lose that skill of remembering to do the plus or minus.
Desmos is really useful.
Yeah, it is very useful. I know.
So
You know, and when I taught an online class, I think I let people use it because some people are going to use it anyway, and it's really hard to proctor that sort of thing. But yeah, technically you gotta know.
okay, cool. That makes a lot of sense. because um, I was just going through all my homework, trying to get caught up with everything, so that way I'm like at
Mhm.
least like thinking about it while before the test.
Yeah.
And 17, I was going through them and I was like, okay, this is correct, this is correct. And then 17, I was like, why am I getting this one wrong? And then
Okay.
I was realizing it after I looked at the
Solutions
worksheet.
manual.
Yeah, that
Yeah.
that they went beyond the x-axis, and I went, duh.
Yeah. Yeah. It's just, you just got to know it's a parabola. What happened to the other part of it?
I
So,
guess I was so used to it being that it would state in the problem that that the x-axis is a bound,
hmm
that I was putting it in subconsciously.
yeah, that's not uncommon.
All right. Well, that I believe is all of my questions I have at this moment. So,
Okay. All
want
right. Well, good luck tomorrow. And I'll see you on Monday.
yes, uh, get better.
Okay.
I
I
definitely,
just feel like I have a cold, but
I
I mean,
know
I definitely
that's
feel
how
worse
I
than
felt with
yesterday.
it.
Really?
It was weird. It was like a cold, but like eh, no fever. It just like
Mhm.
congestion. Um,
Yeah.
Sometimes you get like a cough with it, or like sometimes you don't. I didn't get the cough. My stepdad did though.
hmm
Um, and then on top of it, it gives you like brain fog, so you're not like thinking clearly. That's also probably why you forgot your notes yesterday. Is where
You think so?
probably
Maybe, maybe. I don't know. It just was so random where I was like, yeah, I have this headache. But I mean, I feel run down a lot because I don't get a lot of sleep. I run a lot. I'm just very active. I'm teaching 10 credit hours this summer. I've got 3 kids. So, like, it's not unusual for me to, like, not feel 100%. And it was just a headache. And I was like, oh, I have a headache. I'm going to take some Advil. And then it wasn't until later where my husband was sick that and since I never see him, apparently he'd been sick the whole day, but I didn't know that because I didn't see him the whole day. We did our shift change. I left and then, oh well. So now I feel terrible, but I mean, I don't know. What can you do?
yeah. It's really hard to like catch it beforehand. So
Yeah,
unless you have future sight, it's kind of not possible to be like, oh, I have COVID, I shouldn't go.
right. And then they say you're like most contagious before you even have symptoms. So like, how would you know? And then like by that point, like you can't even try to do the
By
responsible
that
thing because
point,
it's
it's
too late.
really like, well, I interacted with all of you guys. I'm positive, so make sure you don't have it. Good luck.
Sorry. I know, I feel terrible, but like it's not like it's not like, oh my gosh, I tested positive. I'm gonna show up to school now. It was just like, I don't know. I mean, that would be terrible, but
Well, we
I
weren't
don't
like
know.
in super close proximity, so it's not like
Sorry.
horrible. So I think we'll be fine.
Yeah, yeah. Well, I'll see. In case I'm not fine by Monday, I'll send out an email and do another online class. But I mean, if I feel like pretty much fine right now, I have a feeling by Monday I'll be fine. But we'll see.
All right. I'm enjoying the in-person math class a lot better.
Oh, good. Yeah, me too. Me too. hmm I know I was enjoying it so much, and now here we are. But we'll be back. Well, good luck tomorrow. Email me if anything comes up. Okay.
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 Alrighty. You have a nice day.
You too.
Uh, just uh, have a lot of like vitamin D that's supposed to help. And then
Really.
yes,
Okay.
I took NyQuil, and that helped a lot.
Okay.
Um, so
All right.
I don't know.
Yeah, maybe I
Everyone's
should.
different, so I don't know what works and doesn't work for everybody else. But I did NyQuil and I took vitamin D because apparently vitamin D is one of those things that's supposed to help keep it less, I guess.
Okay.
So
I should do the NyQuil because I did wake up at like 6. I always wake up at 6 a.m. usually to run, but I woke up feeling kind of congested and then I had a hard time going back to sleep. So random.
the NyQuil will help with all the congestion stuff. So
Cool. All right. Well, thanks, Jared. You have a good night and good luck tomorrow, and I'll see you Monday. Okay.
All right. See you Monday.
Okay. Bye.